Hello, Gen Chem friends. Thank you for joining me today as we continue our conversation on Chapter 8. What we're specifically going to do in this and in the remaining videos for this chapter is talk about how to use that Lewis dot structure that we learned how to draw for molecules in the previous videos. How can we use that Lewis dot structure to say something not only about the shape, about the geometry of that molecule, but also say something about the properties of that molecule in this chapter with respect to that molecule's polarity. So to do those things, let's first tackle the geometry portion. To be able to link a Lewis dot structure to a particular molecular geometry or shape, we need to introduce a new theorem or a new theory, which is called Vesper. Don't need to know this, but Vesper is an abbreviation for valence shell electron pair repulsion theory. It's a mouthful, which is why we say Vesper. Vesper theory states that the shape of a molecule is due to the domains or the structural electron groups that are attached to a molecule's central atom. And so when determining what those structural electron pairs or domains are, we have to look at not only bonding pairs or atoms attached to the central atom, but we also need to consider lone pairs of electrons on the central atom. It's all about the central atom with Vesper theory and how we're going to use that for molecular shape. Okay. And the theory states that because those atoms and those lone pairs on the central atom, they take up space, they're in orbitals, they arrange in such a way as to minimize repulsions, and so they are arranged in a energy minimum way so that they avoid each other as best as possible. And from that is what a geometry is predicted. So from a particular Lewis dot structure, if we know the number of bonding and non-bonding domains to that central atom, we can write something that is called a Vesper notation that can be linked to a molecular geometry. So in this example, which I'm using, this example uses A's and B's. In this molecule of AB3, this is the Lewis dot structure for AB3, some generic molecule. If I wanted to determine the geometry of that molecule, I need to first determine what its Vesper notation is. And when we do Vesper notations, we use this format AXE. Now, some books use A and B to denote central atom and bonded pairs. MindTap and other texts use this format AXE, which is what I will use in my materials. What does AXE stand for? So when writing a Vesper notation for a Lewis dot structure, A stands for the central atom. So in this AB3, A stands for the central atom. The X stands for the number of bonded groups to that central atom. And so you'll note that X, it doesn't matter if you have something that is a single bond or a double bond or even a triple bonds. All of those count as one domain, one bonded domain. So for this generic molecule, we have 1, 2, 3 bonded groups. So my X, which represents my bonded groups, has a subscript 3 due to those 3 groups. And now I need to take care of or account for the lone pair of electrons, and we account for that with the symbol E. So if you have 1 lone pair of electrons, you would just have a single E in your Vesper notation. If I had 2 lone pairs of electrons on the central atom, it's all about the central atom. If I had 2 lone pairs on that central atom, I would have a subscript 2. So that is how you determine the Vesper notation for a particular Lewis dot structure. You use this AXE notation, A standing for the central atom, X representing the number of bonded groups to that atom. And for the Vesper theory, for that Vesper notation, it doesn't matter if the bonded groups are single, double, or triple bonded, or if they're even identical. Let's say that in this group, this bonded group, I had atom C. I would still, that was different than B. I would still count those all as 3 bonded groups, so it would be AX3. And since I have a lone pair of electrons, a single lone pair of electrons on the central atom, it would be AX3E. That would be the Vesper notation. And why is that so important? To be able to determine from a Lewis dot structure. Once you know the Vesper notation of a molecule, you can look at a chart, which I'll show you shortly, to determine not the electron and the molecular geometries of that molecule. So electron pair geometries just deal with the number of electron domains. Molecular geometry takes into account the positions of the atoms, not the bonding pairs. Okay. What does all that mean? I mention those because many times your electron pair geometry is different than your molecular geometry. This chart, which looking at that, you might think, oh, there's so much information to look at on this chart. This chart illustrates what a particular electron and molecular geometry is for a particular Vesper notation. So I list both of the molecular and electron geometries because you will need that for the mind tap exercises that you do. But I have a great big star here because there is some good news. The great big star is a reminder to me to tell you that for the exam, I will only test you on the corresponding molecular geometry for that particular Vesper notation. So, for example, if I was to look at that AB3 molecule again, we said that its Vesper notation was AX3E, that we can use that to determine the molecular geometry of that molecule. And we will do that in the next video.